Hello everyone, welcome to the NPTEL TA session. Welcome to NPTEL TA session for Introduction to Robotics course. We are in week 9 and as always we will solve some assignment questions which relate to what you are getting currently in your assignments. So these questions are from old assignments. Hopefully they will help you in solving the current assignment questions. So this is a doubt solving session also, but as no one has joined yet, so this is just going to be a question solving session. Okay, so let's begin with the first question. Okay, so the question is, consider the operation of a base filter algorithm as described in the class. The world consists of the state of a door. It is either open or shut. The robot has a single sensor that can sense the state of the door as open or shut. The robot also has an actuator that can push open the door if appropriate. The robot can choose to do nothing, which does not cause any change in state. Given the information below, compute the belief state after the following sequence of actions and observation. Okay, so they have given us that U1 is do nothing and Z1 is shut. So what is U? U is the action and 1 denotes that at what time step. So at t equal to 1, the action is do nothing and the first observation is that it is shut. Okay. The initial belief is denoted by this symbol over here and it is zero point 0.5 for open and 0.5 for shut. So x naught is the initial state. Okay. Then the sensor model tells you that how, with what probability does the sensor detects. So probability that ZT is equal to open. So the measurement is open given that the state was also open. So it's like correct sensing when the state is open is 0.8. So it is 80%. And ZT is equal to shut when XT is equal to open, that is incorrect sensing, that is 0.2. Right? And similarly for when the state is XT is equal to shut. Okay. So that is given in the question. Now, also what is given is the transition model. So suppose you are in the state xt at xt minus 1. So at a previous state, you are like open the so not you are open, the door is open. So and then you take the action push open. Then what will happen to the next state? Okay, so what is the next state of the door? Let's say xt is equal to open. So if the door is already open and you are pushing the door, then it is 100% probability that the door is open. That is what is given. If the door is open and you are again pushing the door, then obviously the probability that the door is shut is 0. Okay. Now what they have given in the transition model is that if the door is shut, xt minus 1 equal to shut, and you are pushing the door open, then the probability of success that P of xt is equal to open given that you have pushed the door and the door was shut is 0.7. So with only 70% chance, you can open a shut door when you choose to open it, right? And then corresponding probability for the shut case is 0.3. Okay, so we have been given all this information. Okay, now we have to comment or we have to choose which of the following option is true. Okay, so what we have to find? we have to find the belief that at x1 whether the door is open or shut, right? So we have been given that at x equal to 0, sorry, t equal to 0, the belief is zero point 0.5 for both open and shut, and the action that we have chosen is do nothing, right? And Z1 is shut. So the sensor measurement says that the door is shut. Okay. So what will be the uh, at t equal to t equal to 1? What is the actual state of the uh, what is the estimated state of the door? Okay. So the measurement says it is shut. The action we perform was do nothing, and initially we don't know, right? It's zero point 0.5 chance that the door was open and zero point 0.5 chance that the door was shut, right? So this is the question. Let me just check whether someone is trying to join or something. Okay. Okay, so let's move on to solve this. Before that, let's look at the formula. So this is the algorithm for Bayes filter. So you pass on the belief at previous time step. Do we have this? We have this, right? We have x0, BEL of x0, right? And we have UT also, and we have ZT, right? So U1 and Z1 is given to us. Now, this is the procedure for all xt. Okay, so for all possible states, we have to do the prediction bell bar xt is equal to integration of probability of xt given ut comma xt minus 1 into belief that belief of xt minus 1 dx, right? And this is called what? This is called the prediction step, right? So we are actually not using any sensor measurement over here. So you can see there is no Z over here, right? And we are just predicting what is going to happen next based on the transition probability. This is the transition probabilities, right? And then in the next step, once we make the prediction bell bar, we use that prediction along with P of ZT given XT. So P of ZT given XT is what? The sensor model, right? So using the sensor model and the prediction, we get the final estimate of XT. Okay. So now let's see how we can compute this for this particular question. Okay, so let's just write the formula down. Bell bar of x1 is equal to summation of, okay, so what is x1? So let's say x1 is equal to open. Eraser is not getting activated. P of x1 equal to open given u1 is equal to, so what is u1 given? Nothing done, right? So nothing. I will not write nothing done. I will just write nothing, comma x0 is equal to open. Okay. This multiplied by bell of x0 is equal to open. Okay. So like this is this step into bell of xt minus 1. And then since we are integrating, we have to integrate over all the states, right? So uh, now we write P of x1 is equal to open given ut equal to open, sorry, ut equal to do nothing, comma x0 equal to shut. Make some space. Into belief of x0 equal to shut. Okay, and this is nothing but belief bar of x1 equal to open. So let's compare with the formula what we have written. So belief of xt equal to open is equal to integration of p of xt equal to open given ut equal to, so here t equal to 1, right? So u1 is given as do nothing, so u1 equal to nothing, x0 t, so is xt minus 1, so this will be x0, and x0 we have to do it for both x0 equal to open and x0 equal to shut, right? Because this both of the things can happen with different probabilities, might have happened, right? So we are not sure about our initial state. So this is the formula. Now what values do we have? So x1 equal to open when the initial state is also open and we have done nothing, right? So this is with what probability? This has to be 1, right? So because it is given that if you don't do anything, then the state remains the same, right? So this is probability 1. Similarly, probability of x1 equal to open when ut is equal to nothing, right? That you did not do anything and the door was shut, so the door will remain shut, right? So probability that the door will remain open given that you did nothing when the door was shut should be 0, right? And belief that x0 is equal to open was given as 0.5. So you get 1 into 0.5 plus 0 into 0.5, that is nothing but 0.5, right? And if x1 is, if the probability of x1 given open is 0.5, right, given that other stuff, then probability of x1 equal to shut given the same other stuff should be what? 1 minus whatever we have calculated, right? So that will also be 0.5. Or you can do the use the formula and calculate it. It will turn out to be same. Okay. So now we have only done the first step, right? So we have done the prediction, and prediction is that uh, the door can be open or closed with the probability of 0.5, and it is no wonder that because the action chosen was nothing, right? So the prediction remains same as the belief of the initial state. Okay, so that way also intuition also tells us that the probability should be zero point 0.5. Okay, so belief should be zero point 0.5. But okay, you can follow the formula and get the answer as shown here. Now let's move on to the correction step, because we have also made the sensor measurement that the door is shut. Okay, so now what is the formula? So let's again go back to the Bayes filter algorithm, and this is the formula. Belief of xt is equal to eta into p of zt given xt into the prediction. So let's write it down. Belief of x1 equal to open is equal to eta into p of z1 open given z1 equal to shut given x1 to belief of the prediction x1 equal to oh, okay, so let's okay, now the screen will be more clearly visible. Okay, so let's move on. So similarly, we can do it for belief that x1 is equal to shut is equal to eta p of z1 equal to shut given. So this was x1 equal to open, right? And this is x1 equal to shut. Okay. So this is written more in more clear font than my handwriting in the slides. But yeah, ignore my handwriting for now. So belief x1, the prediction x1 is equal to shut. Okay, now let's compute this. Uh, so if you add these two equations, what you will get? On the left hand side, you will get belief of x1 equal to open and belief of x1 equal to shut. If you add these two, you should get 1, right? Because either the door will be open or shut. And if both the cases, if you add, then the probability should be 1, right? Now, here you can take eta common and you have P of Z1 equal to shut given X1 equal to open, and this will come from where? The sensor model, right? We'll plug in the values from the sensor model for both these cases. Okay. So what are those values? Let's refer to the values. Yeah. So Z1 is shut given X1 open is 0.2. Z1 shut given X1 equal to shut is 0.9. So 0.2 and 0.9. So let's go back. So 0.2 and the prediction was 0.5 plus eta into 0.9 into 0.5. If you take eta common, what you will get? 0.2 plus 0.9 into 0.5, that is eta, so 0.65, right? So today there is no one to correct my calculations. So let's see, eta is equal to 1 by 0.65. So what is 1 by 0.65? Let's take help of calculator. This is 1.538. Okay, so once we have the value of eta, you can just plug in into the above equations to get the belief. So belief of x1 is equal to open is nothing but 1.538 into zero point 0.2, because that is what our sensor model told us, right? And that into 0.5. So that is nothing but, let's compute, 1.538 into 0.2 to 0.5, that is 0.1538. Okay, we could have done this more smartly, but fine. Okay, let's see if we have made any calculation mistake. If someone is joining. Okay, someone is joining. Hello? Hello? Hello, can you hear me? Okay, the person who joined has left the meeting. So we are back alone. So let's continue. Okay, so I think we have done some calculation mistake. Let's verify. So the probability that Z1 equal to shut, given that X1 is shut, is what? Is 0.9. Z1 shut, given X1 open, is 0.2, right? So that is 1.1. 1.1 into 0.5 is 0.65. Okay, so 1 by 0.65 should be 1.538. Okay, okay, give me a minute, I'll just check my calculation. Yeah, so this is 0.55, right? So this should be 0.55 because 1.1, yeah, but no, 0.5. So this will be what? Eta will be 1 by 0.55, 1 divided by 0.55. This will be 1.818. Now just plug in the right value of eta, 1.18. Now you again compute the belief into 0.2, 0.5. Yeah, so that is 1.18, that is right. This is 1.8 and you will get 0.18. Okay, so I'll go through the entire calculation once. And similarly, if you are getting 0.18 here, what you should get for door shut, it will be 0.82, right? Okay, because 0.18 plus 0.82 is 1. So sum of the probabilities of all the mutually exclusive events should be 1, right? Okay, so now just we'll go through again the entire procedure. Okay, so we started here, the base filter algorithm, and it takes input the belief at the previous state, the current input, and the measurement, right? And for all xt or for all the states, first what we do is the prediction and then we correct our prediction using the sensor model. So for the prediction, the formula is given by the integration of the transition probability for a particular state for going into that state given the input and the previous state multiplied by the belief at the or at the previous time step, right? And here what is everything is known. We know the transition probabilities are given in the question. The previous state belief is also given in the question, and we have to find x1 belief at x1, and this belief is nothing but the prediction. Once we find this, what we will do, we'll use the sensor model given in the question, right? We have the this value also and we have the prediction, so we'll combine the prediction and the sensor model. Okay, and we'll use the sum of the belief trick to find eta, right? Because the sum of belief over all the states is equal to 1. Okay, and by that we get eta value. Okay, and then we'll resubstitute the eta in this formula to get the belief at that particular state. Okay, so it is as simple as that. Just that I messed up 1.5, 1.1 into 0.5 is 0.55, right? So that is the only thing. Otherwise, the question is very simple. So let's see how we did it. The prediction x1 is equal to open is nothing but prediction at x1 equal to open given u1 equal to nothing and x0 equal to open, right? And this was what 1. Okay, from the state transition probability you can see that, and this is given as 0.5 and this is given as 0 and this is 0.5. So we got the prediction as 0.5. Now what we did, we substituted the predictions and the transition probability. So the prediction and the sensor model. The sensor model was given as P1 Z1 equal to shut given X1 equal to open. Okay, so this was given as 0.2, right? And P of Z1 equal to shut and X1 equal to shut was given as 0.9. Okay, so then we had these two equations, we added them, and the left hand side becomes 1. Okay, so we get the value of eta as 1.8, right? We get the value of eta as 1.8. And once we get the value of eta, okay, we resubstitute in the above formula and then we get the right answer. Okay, so next question is exactly same as this question. It's just that now we already have the belief at x1 equal to open and x1 equal to shut, right? And so this is going to be the input, and rest all the things are going to remain same. Only they have to provide us the input and the measurement. So let's see what input and measurement they have given us. So they have said that the input is now push open the door and measurement is that the door is open. So what is going to change? Only the value of the elements. These terms will change. Okay, and that is given in the first question. All those values. Exactly same way we can solve the second question as well. Okay, the same question only, just the values have changed. Okay, instead of x0, we have x1. Okay, from that we have calculated just. Okay, so let's move on to the third question. It says that since the Bayes filter algorithm uses the entire history of observation and action, it does not assume the Markov dynamics for the system. So is this statement true or false? Of course, this statement is false. Why? Because we just saw, right? When we were finding belief of x1, all that we needed was belief at x0. And in the next question, when we are solving for belief at x2, all that we needed was belief at x1, right? And the action at u1 and the measurement at x2, right? So we don't required x0 or like x0 for x2, right? We only required x1. So the entire history is not required, just the past state. One state is enough to abstract the entire history in it. Okay, so that is what the Markov property says. Okay, so we don't require the entire history, just the state can contain the entire history in it. So this statement is false. Okay, because it says that we required entire history and observations and all. Okay, so what is the next question? Which of the following are the valid state variables for Markov model? The total distance traveled since the robot was turned on. Is the stoplight red? The onboard battery level since the last recharge action? The number of times the robot turned left so far? Okay, so if you have understood just the previous question, then you can answer this. Okay, so let's say the total distance traveled since the robot was turned on. So this can be said as a state. Okay, and it is just one value where it can just encapsulate all the distance that has traveled so far. Okay, so this is a state. So there is no problem in this. All right. Is the stoplight red? Okay, this can also be a state for, let's say, uh, so this is like an observer, like what is observation. Okay, and this can be a part of the state if we are saying the robot has to stop at a traffic signal and all. That is not a problem. Onboard battery level since last recharge action. Okay, this can also be a state. So number of times the robot turned left so far. Okay, so okay, so how is this going to help to, like, does this give any useful information? So how many times the robot has turned left? Because okay, so if you are like designing any algorithm for a robot and you want to know its position, okay, it's not sufficient to know like how many times the robot has turned left. It doesn't tell you anything, right? Because then it has also turned right or moved straight and all, and how much left it has moved. Okay, so this alone has no information, right? So okay, so this doesn't make any sense. This is okay. Yeah, but if the state is discrete or the grid is discrete on which the robot is moving, then it can make sense. Like if we say that the robot can, when you say take a left action, then it robot moves only once. Okay, so such kind of thing that uh, for such application, maybe this is a valid state also. Okay, where on a grid, then we can use it. So it is very subjective question. That is what I feel. So it's, I think all answers make sense. But what they are saying is the onboard battery level since last recharge action need not be a valid state variable. But it depends on application, right? So I don't agree with this answer, but okay. This is the answer that battery level since last recharge action is not a valid state variable for Markov model. Okay, let's see the fifth question. Given a noise-free measurement model, it is possible for robot to know exactly where it is in the state space at every instant. Okay, so there is no noise in the measurement. So is it possible for the robot to know exactly where it is in the state space? Okay, so if the so again this okay, so this question is again little bit subjective. Okay, so there is no noise, then that means your measurement is accurate. Okay, so if your measurement is accurate, it's fine. But it also depends on your sensor, right? So what is exactly your sensor is measuring? If your sensor is measuring the position of your robot, okay, and there is such a sensor that let's say if it was a GPS sensor and its job was to measure only your position, okay, and there is no noise or there is no uncertainty, then this is right. The answer is yes. But let's say for position you are using encoders and there is no noise in measurement. Okay, can you get your position correctly? The answer is no. Why? Because there are other factors. Because the motion model is also affecting it, right? So that is the encoders enough are not informative enough to tell you whether the uh, uh, whether you can where you are. You also require the motion model uh, to be used along with the encoders, right? To tell where your robot is. And if there is problem with your motion model, then you cannot know the answer. So if you think in a simplified way, then the answer is yes, because okay, something like where exactly the robot is, so you can assume that okay, it's a position sensor, so there is no noise. Okay, but there are so it's not like that you can measure always the position directly. There are other sensors like encoders, there is lidar, and all those stuff which use other formulas or other mechanisms to come to the your final answer of position. And there is some processing going on after the measurement. Okay, and that processing is based on some principle of physics. And in that principle of physics, if there is some uncertainty in terms of the parameters or in terms of the equations because of some assumptions in the model, then you may not get the right answer. So the proper answer here is no. No, even if your sensor is noise free, uh, you cannot get the exact location of your robot. Okay, so that sums up all our questions. This particular question, I'm not very sure about the answer because okay, the onboard battery level can be a useful state, and since last recharge, they are asking. So that means current battery level only, right? So current battery level can be a useful state in lot of robots. So, and again, number of times the robot has turned left so far in a continuous situation that may not be a very useful state or may not have enough information in it. but on a discrete space, if you are doing any simulation, uh, then this can be a state. So okay, so there is some kind of confusion over here, but okay, I have told you the answer that was expected. Uh, okay, and we have solved this question. So basically, you just follow the base filter algorithm that is given over here. And you remember that first for the prediction step, you have to use the state transition probabilities and the initial belief that is given. And you combine the prediction with the sensor model. And while you combine that, the eta is unknown. So the trick is you sum the two all the states equation, and then you get left hand side is equal to 1, and so you get the value of eta, then you substitute the eta, and that's how you get the final answer. Okay, so since no one has joined yet, I will just end the session, and uh, we'll meet next Sunday. Okay, bye.